All right, we're on a roll with these chain rule problems, so let's keep on rolling. Exponentials. Now, these were really boring when you first saw them in the previous chapter, because without the chain rule, all you can do is the derivative of e to the x is just e to the x. Derivative of a number other than e, but a number, a constant to the x, is just that same number to the x, and you throw on an ln of that same number, just, to make things a little interesting. But the point is, it was really basic. When you ever see e to the x in calculus, it's pretty much always going to have an exponent other than x, which, as we've learned in these previous videos, is, we're going to call that, whatever that exponent is, we're going to call it u, which means we're just going to have a u prime tacked on the end of the usual formula we had before. So derivative of e to the u is e to the u times u prime. So just the derivative of that exponent. And same thing for this, any number to the u. Typically, calculus classes just don't use this that much. It's almost always an e to a variable exponent. It's almost never a number other than e. I'll just throw a couple in here to make you aware of it, but most classes just don't do a lot with this. Anyway, point is, the derivative of c to the u is just c to the u times u prime, and then of course, because you had a c in there instead of an e, you're going to need an ln c to sort of compensate for that. So just remember that e, ln, is just like a log base e. That's all ln means. It's sort of a shortcut. They figured they use log base e so much in science and math and stuff, they just gave it a special name of ln, or the natural log. Or actually, that's probably French or something. It probably means log naturel. But then we just call it natural log. In English, we switch the letters. But point is, ln is just log natural, or natural log. So there you go. So the way to spot the power rule with an exponential, anything besides x in the exponent is going to be your u. So in this case, this guy right here, 2x minus 1, is our u. But really simple to execute this one. It's just going to be e to the 2x minus 1. Derivative of e to the u is just e to the u times u prime, which in this case, derivative of 2x minus 1 is just 2. Because remember, the derivative of e to the u is just e to the u times u prime. So you just whatever you started with, you repeat, and then you drop a 2 on to make it copacetic. And then, as always, I really prefer coefficients to be out front. And I don't know about you or your teacher, but while you probably would have gotten full credit for this, you might not have unless you put the 2 in front instead. What's the deal with this one? Well, once again, we got a u right here, an exponent. So the derivative of e to the x squared is just e to the x squared. Just don't want to forget that u prime, which is, in this case, 2x. So we're going to get 2x times e to the x squared. Just when we take this 2x and move it out front to make it look better, in my opinion, whatever. Your opinion may vary. All right, so non-base e exponentials, same story. The derivative of, it's still going to be the exact same thing. This is our u though, right? So the derivative of this is the same thing, 10 to the 2x minus 1. The only thing is we got to throw in an ln of 10 to make up for the fact that we're not doing an e to a power. We're doing a different number of 10 to a power. And then, last but not least, cannot forget our u prime, which of course in this case is just, again, 2. So I would rearrange the order on this and get 2 ln of 10 times 10 to 2x minus 1, which I now realize pretty much looks worse than the original, but hey. All right, next one. Once again, because we have a 3 here, not an e, that just changes a little bit. The derivative of 3 to the x squared is just 3 to the x squared. We need an ln of 3, though, to make up for the fact that it's not an e. And then we're going to multiply by u prime, which is just 2x. And I'll leave that one as it is, because I don't want to make it look uglier. So that's just a kind of key point. When you're taking the derivative of bases other than e, you got to throw in an ln 3. Turns out in later calculus, when you integrate, so basically reverse derivatives, once again, you're just going to throw in an ln of that base, only in the future you'll divide by that ln. I only mention that now so you keep your eye on it. The difference between exponentials where it's e to the something versus a 5 to the something is just you got to throw in an ln 5 to sort of make up for the sin of not using e. All right, more exponent examples, more e examples. So the derivative of e to the sine x, it's just itself. E to the anything, its derivative, is just that same e to the something. So e to the sine x. Bam, are we done? No, because this was a u, right? Sine x is our u. So we now got to multiply by u prime, which in this case is cosine x. Again, though, not bad. Same thing here. Is this one a little bit nastier, though? This one actually is a little bit harder. Still, the derivative of e to the anything is just e to that same thing, so it's cosine of x squared. But what makes this one juicy is that now when I want to find u prime, I know you guys probably hate it by now when I underline u prime because that probably means we're going to have to use the chain rule again. Because the problem is that now I need to multiply by the derivative of the exponent, right? Which is cosine x squared. But that's a chain rule problem on its own. Because the derivative of cosine x squared is going to be negative sine of x squared times its own little u prime. Because we have an x squared here, which means we got to multiply by 2x. So we had just to find u prime from the original problem, we had to use the chain rule to find the derivative of that cosine x squared term. So just simplifying this, it's negative 2x times sine of x squared. And now this is what I can plug in right there. So u prime I just figured out is negative 2x times sine of x squared. All right, super gnarly. But that's what we're going to call the nested chain rule. Because we knew right away when we saw that e had a variable, had an exponent other than just x, we knew we'd have to use chain rule. But then in finding the derivative of that u prime, we had to use the chain rule yet again on just that exponent. So, crazy stuff. I know it's confusing, but if you go through it 20 times, it turns out to kind of become second nature. So, I'm introducing all this. I'm sort of assuming you're practicing along with me, or maybe you're pausing the video and working on your own and then watching the video, because really that's the way to go. You're not going to learn this just by watching. You need to sit down and actually get confused and then try and unconfuse yourself. That's how you learn stuff. So if you just watch the videos, it's not probably going to get you the A that you're looking for. It might help you pass. But you should really be working these along with me. So natural exponential examples, a few more. Once again, just looking at this, I'm seeing some nastiness here. I'm guessing this is a nested power rule problem. Oh well, we'll get to that when we come to it. So first of all, the derivative of e to the anything is e to the anything, so e to the sine squared 3x. But now I got to multiply by u prime, and that's where I think I'm going to get in trouble, because when I take the derivative of this thing, that is a power rule on a sine function. So right away I'm like, oh man, that's a power rule. So I'll rewrite, so u is, I'm going to rewrite this as sine 3x quantity squared, just to make it real obvious. Because that little square on the shoulder of the sine, all that means is the sine of whatever, all that is squared, like you're squaring the sine. So that means the u prime is going to equal old power 2 times this cosine, derivative of sine is cosine of 3x. And then I got to multiply by the derivative of the argument, which in this case is 3x. So the derivative of 3x right there is just 3. So that gives me 6 cosine of 3x. All right, so that's my u prime, and that's what goes in there. 6 cosine of 3x, and, you know, I don't know. That's probably simplified enough to get full credit. All right, is this one worse than the one we just did or not? Well, it's a nested chain rule, but once you're in nested chain rules, the only thing that makes it worse is we have a secant instead of a sine or cosine. You know, secant formula is just a little bit messier. All right, so the derivative of e to the anything is exactly that same e to the anything. So e to the sine, secant of x squared. But now I got to multiply by u prime. So that means I got to work this, hey, what's the derivative of secant of x squared? Well, let's see, u equals secant of x squared, so that means the u prime, the thing I want to plug in to my big problem, is going to be the derivative of secant x squared is secant x squared tangent x squared. and then you got to multiply by the u prime of this little mini problem. So since this was my little, the secant is of x squared, therefore I got to drop the derivative of that on the end here, which is 2x. All right, so now I'm going to take all this stuff and plug it in right there for u prime, since this was u prime. So, man, I got a secant squared. Oops, secant of x squared tangent of x squared times 2x. Now, if you really want to make this look pretty, maybe take the 2x and put it out front. Not that that looks great either, but point is, you can rearrange this a little bit, but you don't need to do a lot. All right. So what do I mean? When e is u? So these right here, you're looking at it and you might be like, wow, I see two sort of interesting derivatives I've got to take, or two sort of messy ones. I've got an exponential, which is weird, and I also have a trig function, which is weird. Well, it turns out that this is actually a derivative of a sine problem, and then just finding u is going to be the exponential part. So this is really just u. This e to the 3x is just u of a sine u problem. So what's the derivative of sine of u? Well, it's cosine of that same u, right? So it's cosine of e to the 3x. Then I'm going to multiply it by u prime. But what is u prime? Well, it's the derivative of e to 3x. Which is e to 3x times the derivative of the exponent. So that's just 3. All right, so this is what goes up here. So we get 3 times e to 3x. Ooh. Doesn't look too bad. There's not a lot I can do here. And then because this is sort of within the parentheses behind the cosine, and this is not, I can't combine these e terms or anything. I'm just kind of stuck with what I got. So, I don't know, maybe walk away at this point. Maybe move the 3 out in front of the cosine. Whatever floats your boat. Well, let's do another one. Derivative of cosine of anything is negative sine of that same thing. So negative sine of e to the secant x. All right, times u prime. Where this was our u, right? Because it was cosine of this, so that makes this our u. But if that's our u, the derivative of that is going to be, it's an exponential, so the derivative is the same exponential, so e to the secant x. Then we got to multiply by the derivative of the exponent of the exponential, which is, so derivative of secant is secant x tan x. All right, once again we got a mess, but it's like not a lot we can do in terms of combining things. But again, this was a nested chain rule because we need to find the derivative of cosine of a mess, you got to use the chain rule once. But then in calculating u prime of, this was our u, so in calculating u prime, it's like, oh man, that's an exponential with an exponent that's not x, it's secant x. So that means just to find u prime, we had to do a chain rule again, just on the e to the secant x. So that's your nested chain rule. Don't worry, we're going to see these lots more. We got a hard chain rule video coming up, and you'll continue to see the chain rule throughout calculus. So just consider this a warm-up. Like I said, though, practice, practice, practice. The only way to get these down is to practice them a lot, work them on your own, and then check your answers. So either work the ones in the videos here on your own, and then check them against the videos and see how I did it if you didn't get the same answer I got. Or you can work ones in your book and just look in the back, do the odd ones where you can see the answer in the back and just see if you can get the answer that's in the back without sort of looking ahead first. Because on a test, obviously, you won't have the answer, so you just want to get in the habit of working the problem, seeing if you're right, so you can sort of get all this chain rule stuff down. Because it is tricky, it is confusing, you can get lost in the weeds as you go. It's like chain rule inside a chain rule inside a chain rule. But, we'll get to that in the hard chain rule video. These are pretty hard, though, so there's no such thing as an easy chain rule problem.